Linear approximation is the idea that we can use a linear equation to approximate a function. Here's the idea. It's a fascinating concept called local linearity. We've talked about it before and looking at other functions, but it's that idea that when you zoom in on a function, it actually looks quite linear. I've drawn a segment on this globe here, and you can see it actually, the segment of course is flat, but the Earth is not. And so it doesn't exactly follow the curvature of the Earth. But for a small region, the line is a good model for the Earth, just for a small region. Of course, if I extend that line out, it no longer is a good representation of the curvature of the Earth. But as long as I stay local, keep that tangent segment short and small, then it makes a good approximation for function values of this curve near the tangent point. You can kind of see that in this sketch of the unit circle. What I have done is zoomed in on this point here, 1, 0. So here's the unit circle, and then I zoom in on one small section of it, and you can see the curvature is still evident, but it does look a little flatter. And then I zoom in on this box here, and the curvature is still there. You can see a little bit at the top and the bottom, but here it looks really flat. And then one more zooming in, it looks completely flat. That's the local linearity of a curved surface. So using that idea, why not use the equation of this line just for a small region near 1, 0? I could use the equation of this line to approximate values instead of trying to figure out the values using the actual function. But I can only do that for a super zoomed in region of the curve. Well, let's see how this plays out. So we're going to take a look at the square root function, and we're going to look at it near 4, 2. I do want to draw the tangent line at 4, 2, so I need to calculate that. All right, so the x and y value have been defined on the curve, and now we need the slope of the tangent line at that point. So I need my first derivative. Whoops, let me undo that and get it off of the ruler. And so let's calculate the first derivative so we can get that tangent slope. The derivative of square root of x is 1 over 2 square root of x. And now I want to evaluate that at the point when x is equal to 4. So that's 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. All right, so the slope of the tangent line is 1/4 at the point 4, 2. So now we can write the equation of the tangent line. Y minus 2 equals the tangent slope of 1/4 times x minus 4. And of course, we always put it in point slope form. All right, now I'm going to do one extra step here. I'm going to put it into function form and move this minus 2 to the other side of the equal sign. Just solve for y. So y is equal to 2 plus 1/4 x minus 4. Now I do this so I can get it into function form. And then it's very common to take this y and to write it in function form, give it a name, and it's common to use like something like t for tangent line or l for linear approximation. So I'm going to go ahead and use l. All right, so replacing the y with L of x, I get L of x is equal to 2 plus 1/4 x minus 4. All right, so this is my linear approximation. A line, is actually the tangent line at 4, 2. Let's go ahead and we're going to graph this and just draw a little zoom in sketch. So I've got it graphed here on Desmos, and the point 4, 2 is plotted, and you can see the curve y equals square root of x, and here is the tangent line. All right, so you can see there's a big gap right here. So let's go ahead and sketch that. So here's the graph, and maybe I'll give it some color. So here's the square root function. And then I'm going to plot 4, 2. And then I draw the tangent line at that point. Oops, there we go. Fix that a little bit. Okay, so there's my tangent line. All right, so when we zoom in on that, let's take a look and see what happens. All right, so zooming in on that point. All right, you can see that there's still some gap between the function on both sides, but there's a large portion where the tangent line seems to be right on top of the square root function. So we can go ahead and close that off. We can go ahead and make a sketch of that. So I'm at x equals 4. And there is some curvature to the square root graph. And then I draw my tangent line. And I could see that there's a larger region where it's tangent, but there's a little bit of gap on each of the ends. And then I'm going to do another zoom in. Go here, let's do another zoom in. And you can see there's a much greater region. I'll even zoom in even further just for fun. There it looks almost completely linear. Just on the very ends, can we see the gap? So there's that local linearity in action. Let's go ahead and make one more sketch of that. So the square root graph barely looks curved at all. And zooming in, that tangent line seems to just follow right along with it. So that's the main idea of local linearity. All right, let's take a look at an example where we use the linear approximation function to evaluate a function point. So to do that, the process is that you calculate using point slope form the equation of the tangent line. And then again, just to remind you, we're going to make a slight adjustment and we're going to write it in function form. So I have to solve for y. And that means that I'm going to add the y value to the other side. So I get y equals f of a plus f prime of a. That's the slope, times x minus a. All right, so a is the value, this is the point, the tangent point. This is at x equals a, we are calculating the tangent line. So at a comma f of a, that's this point here, that's the point of tangency. All right, so this will be our linear approximation, and we usually just convert it to function form by naming it L of x. You can call it f of x. Well, you can't call it f of x because f of x is the name of the function. I'm going to call my function that we're going to be approximating. So give it some other name, or to make sure it doesn't match the function that's being discussed in the problem. Just make sure it's something else. So we're going to use L of x. All right, so L of x is equal to the y value at a plus the slope at a, x equals a, times x minus a. All right, so this is what we use to create a linear approximation. It's just the equation of the tangent line in function form. All right, so we're going to approximate the value of the square root of 3.9. Now, to begin, I need to name a function that we're working with, and it should be obvious we're doing the square root function. So I will begin by identifying my function. I'm going to let f of x be the square root of x. Now, the next thing I'm going to want to do is to pick a value that I can take the square root of. Now, 3.9 is very close to 4. So I'm going to let a be 4. All right, remember, we have to pick something very close to 3.9 that we could calculate. All right, so I can take square root of 4, so I'm going to use that. All right, and then just like we did we already did this on the previous page. Remember that we did this at a equals 4. So first off, f of 4 is the value of 2, and f prime of 4, we did that, was 1 over 2 times the square root of 4. Remember that? All right, so that's 1/4. And then we got a tangent line approximation. So L of x would be equal to the y value, 2, plus the slope, plus 1/4, times x minus a, and the a we chose was 4. All right, now we are going to now approximate 3.9 using this tangent line. So I'm going to evaluate L of 3.9, plug it into the linear approximation, and that gives me 2 plus 1/4 of 3.9 minus 4. All right, and so now I evaluate that, 2 plus 1/4. All right, well, 3.9 minus 4, that's negative 1/10. So I'll write it in this form so I can multiply it by the fraction. And so that would be 2, that would be minus 1/40. And a common denominator would be 40. So 2 would be 80 over 40. Oops. 80 over 40 minus 1 over 40. And you can see we're getting 79/40 as our approximation. Okay, if you put that on a calculator, that comes out to be 1.975. And so just for fun, I actually plugged in square root of 3.9 on my calculator, and it gives me a more precise approximation. So I thought we would compare it. This one's 1.9748, took it out to 4 places. And in calculus, we need to be accurate up to 3 decimal places. So if you compare, the ones are exactly the same. The tenths place are both 9s. The hundredths are both 7. And then rounding this to 5, even to the thousandths place, there's this level of accuracy. So this linear approximation was very easy to hand calculate without a calculator, and it came up with a value very close to the calculator's approximation, which is done with greater accuracy.